Hello students, let us recall behavior of a current carrying loop when placed in an external magnetic field. Here I am showing a current carrying loop. The current sense is shown with these arrows. Now what will be the magnetic moment for such a coil? First point to note is the area vector. How do you get the area vector for the loop? You have to curl your fingers along the sense of current and then our thumb points the area vector. So, in this situation area is pointing towards right. Now, the magnetic moment is defined as the current into the area vector. M bar is given by I into area vector. Area vector is pi r square because it is a circular ring, a current carrying loop, it is a ring. So, the current into pi r square into area cap, this gives the direction unit vector. In this case, one thing you need to note here is the coil must be planar. It may be irregular in shape, but it should be in a plane. So, if this is the plane, the coil can be irregular also. In such a case, the magnetic moment is given by the current which it is carrying into the area vector. So, area vector is curl your fingers along the sense of current. Here area will be pointing outwards like this. So, if this is A1 bar, say, the magnetic moment in this case is given by I into A1 bar. So, that is how you calculate the magnetic moment. One thing to notice here is the magnetic moment is also a vector. So, as soon as you identify the sense of current, you should be able to identify the magnetic moment vector clearly. So, let us do an exercise now. I am showing 4 scenarios here, 4 are independent scenarios. For this situation, let us calculate the magnetic moment. The important thing is to find the direction of the magnetic moment. So, what do you do? First curl your fingers along the current sense, then our thumb points the magnetic moment vector. So, this is A bar and magnetic moment is also directed along A bar. For this scenario, curl your fingers, use right hand, curl your fingers, thumb points magnetic moment. Let us say this is a magnetic moment obtained for a current carrying loop. Now, the question here is how do you visualize the current carrying by the loop. So, if this is the magnetic moment, place your thumb along that direction, now curl your fingers, that will give you the sense of current. So, current should be around this magnetic moment vector. So, you can draw a ring. So, it is going into the board here and coming out of the board here. So, it is around the magnetic moment vector in this way. Similarly, let us try this. So, here the current will be curling like this. So, the magnetic moment vector, if it points like this, current sense is it is coming out of the board here, it is going into the board here. So, that is how you identify the magnetic moment for the given coil. Once you identify the magnetic moment vector, you can visualize the magnetic moment vector alone. You can forget about the current carrying loop and solve any problem. So, that is how they are important. So, let us see how such a current carrying loop experiences torque when placed in an external magnetic field. In this scenario, the horizontal magnetic field here shown is with these arrows. The magnetic field is directed towards right in the space. It is pointing towards right. Now, when a coil is placed, a current carrying coil is placed in such a magnetic field, it experiences torque. So, the torque equation can be calculated by using this relation, torque is given by m cross b. But let us identify all the vectors, essential vectors here. M bar will be pointing in this direction, you have to curl your fingers in the sense of current direction, then thumb points m bar. So, R m bar is here. I hope it is clear to you. Now, imagining the entire situation in 3D is a little difficult. So, let us reduce it to a 2D figure. So, this planar loop, the current carrying loop is represented by this system here. I am using a dot here and a cross here, indicating that the current is going into the board at this place, it is circulating like this. So, it is going into the board at this place and coming out of the board at this location. So, you can represent the loop in this manner. The current is coming out here, going in here, and the loop is something like placed in this sense. So, you will be able to see it as a line, you will not be able to see it as a ring. So, that is our line here, dotted line. Now, the magnetic moment vector is pointing away from the center, perpendicular to the plane. So, it is pointing in this direction, m bar. Now, you will get an idea of the angle, that is this m bar making with the B, the magnetic field vector. So, this theta is what we need, because when we calculate m cross B, it is given by mb sin theta and with a unit vector for the cross product. So, we will have to calculate the magnitude, then you will require the sin theta, and this theta is the angle between the magnetic moment vector and the horizontal magnetic field. Here it is horizontal, it can be pointing in any direction, but here it is horizontal. So, you will calculate the magnitude m into b, but in this case our magnetic moment is given by current into the area vector. So, I into the area is the plane we have here is the loop we have here is circular. So, it is pi r square. So, that is why I into pi r square into b into sin theta, and the direction is given by cross product rule. So, you have to take m cross b and our thumb points the product. So, our product, the torque here is pointed inwards, curl your fingers from m to b, the thumb points the cross product. So, our torque is directed inwards. What does it mean? Now, in this situation, the loop has a tendency to rotate clockwise. So, if you place it like this and leave it, because of this arrangement, it will experience a torque which will make the loop rotate about one of its diameter given by z dash line here. So, this coil will now have a tendency to rotate clockwise along its diameter. So, if it is like this, it will have a tendency to rotate along the diameter. So, if you want to calculate the angular acceleration in this particular case, you can equate torque to I alpha, but in this case you have to substitute for I correctly. You should not substitute m r square, because m r square is the moment of inertia for the ring when the axis is perpendicular to the plane, but here the axis is along the diameter. So, the moment of inertia will be m r square by 2. So, m r square by 2 into alpha, when you equate it to this, you can find alpha. So, this is how you approach a problem which involves the rotation of the coil when it is placed in the magnetic field. It will experience rotation because it will experience torque. So, let us see how torque acts on this coil and how potential energy is developed in this situation. In this situation, the magnetic moment vector is pointing like this and the B is pointed towards right, the same scenario, and they are making an angle theta with respect to each other. The angle between them is theta. Now, because of this torque, the coil has a tendency to rotate clockwise, but if you do not want to make the coil rotate, you will have to apply an external torque which balances this torque. So, the torque here applied by the magnetic field is causing the coil to rotate clockwise. Torque due to magnetic field has a clockwise sense of rotation. It will tend to rotate the coil clockwise. So, if you balance this torque, you need to apply a torque on the coil in anti-clockwise sense. So, the torque due to external agent will be anti-clockwise. So, if they both match in magnitude, the coil will stay in the given position, otherwise it will have the tendency to rotate and it will get angular acceleration. So, let us say we are holding the coil by applying a torque which is exactly equal to the torque due to magnetic field in terms of magnitude, but which has an opposite sense of rotation, anti-clockwise sense. Now, if you slightly increase this torque so that the coil now rotates by an angle d theta, a very small angle. The coil is placed like this. So, now I am applying an external torque only very slightly greater than the torque due to magnetic field. So, it will start to rotate anti-clockwise very slowly. Now, in such a situation, whatever the work we do is stored as potential energy in the system. That is the main idea. So, the work done by external agent when rotated slowly is stored as potential energy. How do you get the expression for the potential energy? You have to calculate the work done by the external torque. So, external torque in this case is almost equal to mb sin theta. It is equal to the torque due to magnetic field. We are increasing it only very slightly because we want to rotate it very slowly. So, it is almost equal to mb sin theta. We will take it equal to mb sin theta, and torque will be in anti-clockwise sense pointing outwards, and we have to rotate this loop by d theta. So, d theta is also taken as a vector. The small angles can be considered as vectors. It is pointing outwards because it has a sense of anti-clockwise rotation. So, both are pointing outwards. Now, the work dW by external agent, the small work done in the situation, is given by torque into the angle, the dot product of these two vectors. So, this gives you mb sin theta and d theta. So, if you want to rotate the coil in this situation by a small angle d theta very slowly, whatever the work you do is stored as potential energy. So, using this, let us calculate the potential energy for any angle theta. Now, the small work done by the external agent is stored as potential energy, that is to increase the potential energy by a small amount. So, the increment in the potential energy is nothing but the work done by the external agent. Keep this point in mind. When it is rotated slowly, this is true. Okay. So, if you integrate this expression, you have rotated it now from theta 1 to theta 2. You have slowly rotated it so that now it makes an angle theta 2. Initially, it was at theta 1. Now, in this scenario, we will calculate the potential energy stored. So, it is given by the integral of the work done. So, integrated from theta 1 to theta 2, the torque is mb sin theta and the angle is d theta. So, the dot product is mb sin theta d theta. This is the work done. So, if you integrate this expression, you get this result. The increment in potential energy at the situation theta 2 minus potential energy in the situation when it is placed at an angle theta 1. So, the difference in the potential energies is this value. Now, we have an assumption here, we will make a reference point. Our reference in these scenario is always for the angle when theta is equal to 90 degrees, we say that the potential energy of the system is 0. It is a convention, it is just for a reference. So, whenever the angle between the m bar and the b bar is 90 degrees, when the theta is 90 degrees, we assume that the potential energy in that situation is 0. That is our reference value. So, in this situation, u for 90 degrees angle is 0. So, by making use of this, let us substitute for theta 1 90 degrees and theta 2 be any particular angle theta. So, this term now reduces to the difference in potential energies for the situation when it is in angle theta minus the potential energy when it is making an angle 90 degrees. So, the difference in the potential energy is now given by minus mb cos theta minus cos 90, you substitute theta 1 as 90 degrees, but this is 0. So, we get the expression u theta as minus mb cos theta. What does this imply? By treating this configuration as the reference with respect to that situation, now the potential energy of the system for any angle theta can be given by this expression. So, minus mb cos theta gives you potential energy only because you have taken the reference in this situation as 0 for 90 degrees angle. This is very important thing. So, our idea finally comes to this point where the current carrying loop is this shown by these arrows. Now, the magnetic moment vector is m bar and the magnetic field here is pointed towards right. So, in this scenario you can say that the system has stored some potential energy and that is equal to minus mb cos theta. Let us find the values for torque and the potential energy in 3 situations. They are very important in solving problems. So, first situation is when the angle between the magnetic field and the magnetic moment vector is 0 degrees. That means they are pointing in the same direction. The coil is placed in the vertical plane. So, the magnetic moment vector points towards the right here for this sense of current. Now, when the angle is 0 degrees, the torque is mb sin theta, sin 0 is 0. So, the torque will be 0 and the potential energy is given by minus mb cos theta and theta is 0. So, it is minus mb. For 90 degrees, the torque will be mb and the potential energy will be 0. This is 0 because we have taken it as a reference. You should remember this. It is 0 because we have considered it to be 0. This is our reference. Compared to this configuration, we will define the potential energy for any other configuration. So, this is our reference. Now, when the theta is 180 degrees, that means the coil has rotated 180 degrees. Now, the magnetic moment vector is pointing towards left and b bar is towards right. The angle between them is 180 degrees. The torque will be 0 again and potential energy will be plus mb. So, you should note this, the potential energy is highest at this angle. So, for this configuration the potential energy of the system is highest and for this configuration the potential energy of the system is lowest. So, the potential energy here varies from plus mb to minus mb. 0 comes when the theta is 90 degrees and these two configurations they are equilibrium positions. Why equilibrium? Because the torque in that situation is 0. The torque here is 0 and the torque here is also 0. That means, if you place the loop in the vertical plane such that the magnetic moment is either towards right or towards left, it will be in equilibrium. The net torque acting by the magnetic field will be 0. So, it will not rotate. But the difference between these two is this is stable equilibrium position and this is unstable equilibrium position. That means, if you place the coil in this configuration and if you tilt it, it will tend to regain its position. But in this scenario, if you displace it or rotate it very slightly, it will never regain its position. It will go away from it. It is unstable equilibrium. And the potential energy ranges from plus mb to minus mb, the least. These are the important points here.